I've got two integrals up here on the board, and I'm going to evaluate this first one without doing any calculations. I'm just going to look at it. I'm going to say that's 0 by symmetry. Now, what does that mean? Well, I'm going to start by just drawing a picture of the region over which we're integrating. So I can see over here y is varying from -1 to 1, and so is x. So we're basically just integrating over this square in the xy plane. Now that square has some very nice symmetry to it. I can see it's symmetric about the y-axis. The left side is exactly the same size and shape as the right side. It's also symmetric about the x-axis. The top half is exactly the same size and shape as the bottom half. Now, in concluding that the integral is going to be 0, only one of those things is actually useful. What's useful in this case is the symmetry about the y-axis, and let me show you why. The y-axis is going to break this up into two halves. So there's the left side and the right side. Now, if I pick a point on the right side, I'm just going to label that as an arbitrary point xy. Now, I happen to have put that up here, where x and y are both positive. I could just as well have put it down here, where x would still be positive, but y would be negative. So the presence or absence of a plus or minus sign isn't telling me the sign of x and y. I'm saying, I'm calling that point xy. I can see if I actually put it there, x and y are both positive. But if I'm thinking if this is an arbitrary point on the right side, I could put it here. X would still be positive, y would be negative. They're variable names. Okay. But what I want to do is take a look, take advantage of this symmetry, and say this point would have a mirror image point over here. And that point would have the same y value, because it's at the same height, but it would have the opposite x value. And that would work equally well if we were down here. The mirror image point has the same y, but the opposite x. Now, that's relevant because that's going to tell me that the height, the z value that I'm attaching to these points, are exact opposites. Because I'm going to get the same thing when I square the same y value, but here I'm multiplying by x, here I'm multiplying by the opposite of x. So the heights that I'm getting on the left side are exactly the opposite of the heights that I'm getting on the right side. That means those signed volumes are going to cancel each other out. Okay. In order to conclude that this is 0 by symmetry, I need both of them. Volume is area of the base times the height. So I've got to have that the bases are essentially the same. The bases are the same size and shape, but the heights are exact opposites. The heights corresponding to mirror image points must be exact opposites. So I need to have symmetry in the base and symmetry in the height in order to be able to use that. All right, let's take a look at our next function and see if we can use symmetry here or not. So here, I'm integrating over a region where x is going from 0 to 2, and y is going from -3 to 3. So here, I only have one type of symmetry in my region. It's not symmetric about the y-axis, but it is still symmetric about the x-axis. The top and the bottom are exactly the same size and shape. Let's take a look at the heights. If I have a point here, x, y, the mirror image point on the bottom half would have the same x, but the opposite y value. Okay, so, and that's why I'm always checking with symmetry about one of the axes. This is symmetric about the line x equals 1, but that's not going to help me because I don't have opposite x values on either side of that line. Okay, so if I now look at my z values, that's x squared plus y squared. The fact that that's the opposite y value is not going to give me the opposite height, because this z value here is always going to be non-negative. I'm not getting opposite heights to cancel each other out. So I can't simply say that it's 0 by symmetry. But I can do something that would be a little bit helpful. I can see that these mirror image points are going to give me the same z value. So if I wanted to, I could just work over this top half and then double it, because I'm going to be getting another copy of it on the bottom half. So I can say this is 2 copies of the integral from 0 to 2, integral from 0 to 3. To get just the top half, instead of y going from -3 to 3, I'm just going to go from 0 to 3. And then we've got x squared plus y squared dy by dx. And I would want to, just to show my work, say that I'm doing this by symmetry. Okay. Now, I still have to actually do the integration, but that made things a little bit easier because it allows me to use 0 as one of my y limits of integration, whereas here I was using -3. So it just makes my limits of integration a little bit easier. It's not quite as quick as when I get exactly opposite things and can just conclude that the integral is 0, but it is kind of nice. So this is 2 copies of integral from 0 to 2. Let's do the integration with respect to y. So I'm going to get x squared y plus y cubed over 3, and that's evaluated between 3 and 0, and then we still have our integration to do with respect to x. Okay, so that's 2 copies of the integral from 0 to 2. Let's see, when I plug in 3 for y, I'm going to get 3x squared plus, that's going to be 27 divided by 3 is 9. And then when I plug in 0 for y, both of those terms just go to 0. Okay, so that's 2 copies of, we're going to get 3x cubed over 3, that's nice, that's just x cubed, plus 9x, and that's evaluated between 2 and 0. So that's 2 copies of 2 cubed is 8, plus 9 times 2 is 18, minus, when I plug in 0, I do just get 0. Let's see, oh dear, 8 plus 18, it's going to be 26, and 2 times 26 is going to be 52. Okay, so saved us a little bit of time. Okay, I want to just show you one more example, though, as a word of caution. I'm going to keep those same limits of integration from 0 to 2, from -3 to 3, and that was dy dx. Let's just look at y squared e to the xy. Now, I'm not actually going to work out this problem because it's kind of a pain, okay? But what I am going to do is show you that we don't have a shortcut with symmetry, okay? And I'm letting you know that I'm not actually going to work this one out, because otherwise you could say, oh, maybe I should do that as an exercise. And in general, I think that's a good thing. Here, I just picked this because of the fact that I can't use symmetry. Now, it's the same region, so it's still a region that's symmetric about the y-axis. The top half of the region is exactly the same size and shape as the bottom half. And I have a point here, xy. Its mirror image point then would have the same x but the opposite y. But if I plug in here, I don't get exactly the same thing on the top point and the bottom point, because the y squared will be the same, but the e to the xy will be different. But I'm also not getting the exact opposite thing, because this factor is exactly the same. And also, with an exponential, e to a positive number is not the same thing as the opposite of e to a negative number. So even if I didn't have the y squared here, e to the xy, that would actually be enough for me to say, no, that's not the same, and that's not the opposite of e to the opposite of xy. That would give me the reciprocal, not the opposite. So, be very careful. I sometimes see students who see, oh, my region has symmetry, and they conclude that the integral is 0, or that they can just double the integral over half of it. You do have to also check that you have symmetry in the heights, or the z-values. If they're exactly the same for mirror image points, you can work over half of the region and double it. If they're exactly the opposite, then you're good to go with that. But if not, it's not going to work.